So we have the next session for this afternoon by Michael Christian. Did I pronounce it right? So Michael Christen is a long-time open source developer. With over 20 years of experience building tools for the FOSS community. As a maintainer of YACY.net, a decentralized search engine, and Suzy.ai, an open source conversational AI, he cares about open knowledge and DIY tech. And this afternoon, he'll be talking all about ChatGPT.
And he introduced he was thinking about a way to win with roulette. So he wanted to compute how the stream of numbers, the stream of numbers that appeared in roulette. So he computed the likelihood as well, and he found out if it's possible and Martin Minsky wrote a book about the perceptron and proved that it's not useful for anything. So a long time went by until someone else, we will see, discovered how to do this actually in a good way. At this time, there was already a discussion about what is artificial intelligence, can artificial intelligence think, is it able to understand, and so on. And philosopher John Searle introduced the idea of the Chinese room. It's a little bit strange to present the Chinese room in Asia, but that's what he called it. He said an artificial intelligence is something like a room where I pass in a letter full of strange symbols. Let's say they are Chinese symbols. And then this room is full of books, and there's an operator who reads the books and has some instructions what to do with all these strange symbols, and all these books show him that he has to put in some other strange symbols, and he passes this out, and then what he passes out is a message which actually makes sense. But he says, the person in the room doesn't understand anything of what he did in the room. He was just organizing these books, and the person didn't understand anything about this. Therefore, the whole machine, the room, doesn't understand anything. I think this is a very strange argument because, in my point of view, it could be possible that the room has understanding about the operator, but at this time, nobody was thinking about this. But I think it's a very good example to describe how LLMs work. And we will use this argument later. Now, we have Geoffrey Hinton. And Geoffrey Hinton got the Nobel Prize last year, not especially for neural networks as he did it, and the work he did with back propagation, but he did something before which was actually related to physics, and therefore the physics Nobel Prize was appropriate. You can think about this in a different way if you're a physicist, but what he picked up was the and he introduced a mechanism that was not only able to compute everything that the perceptron wasn't able, but he introduced also a learning process so that the network was able to learn to perform a specific task. He also introduced the autoencoder, which is a special topology in a neural network. If you make a small section in the network, then the network is forced to do an abstraction there. So therefore, he found a way that the neural network is not only performing a computation, but is also able to do an abstraction of the actual task. So if we want to go forward, we have to think about some mathematics. We need a little bit of linear algebra, and most of you should have linear algebra in school. So everything which is on this slide, you should know everything of this. I don't expect that you know what's a vector, what's a matrix, how to multiply a matrix, but I just want to keep it in mind because there's something very special about the dot product or the scalar product. This is an important thing. The scalar product is computed by multiplying some two vectors, and it gives you the cosinus distance between those vectors. That means, are these vectors orthogonal to each other? Then the product is 0, and we have also bias
And activation function. The activation function makes this nonlinear. The activation function must be a nonlinear function. And so you don't need this pending anymore. It's only linear algebra. What we are doing is static multiplication, and you can write this in a very short form. And that's the form we want to use further on. So if you want to do an inference, then you just have to do the calculation for
likelihood that a special event happens. Like this is 10% likelihood, it's 27% likelihood, it's 3% likelihood, and if you compute the sum of it, then you have always 1. Activation function you can use everywhere in the talk. So, 1996, a student from Jung Schmidhuber, Sepp Hochreiter, wrote a master thesis where he had a strange idea that he wants to feed in the output of a network to the input again. So it creates a recurrent neural network. It's moving into a loop, and what it introduces is some kind of memory. This kind of network has a memory of signals it has seen before, because it computes depending on the signal before. And both did some research and found out that there's a problem to solve, like a machine learning problem, and what came out was the LSTM, long short jump memory, which is something that was used the next 20 years. It's still relevant. It is what enabled many companies, large companies, to train networks that have been able to do translations, for example. And this was the major breakthrough which introduced the computation of sequences with neural networks. So next thing that happened was convolutional networks. What we see here is a very young Jan person here, who puts a paper under the camera, and the computer recognizes the numbers and shows this. Jan Kuhn is a student from Geoffrey Hinton, and he did more research, and he developed convolutional networks, which is a special shape of a neural networks, which is able to do pattern recognition. And then 2017, I think, he was asked by Mark Zuckerberg if he wants to start a science department at Facebook. And he said yes, but only if everything that we produce will be open source. So this is a major point, because we have seen the first large language models coming from Meta, and maybe because he got this position. Oh, I don't have this slide here. Okay. Because he got the position because he said everything must be open source. Maybe that was the reason we got large language models. Next is Joshua Bengio, and I think Bengio should have got the Nobel Prize for what he did, because he said if we want to put in characters in the streams that we want to predict, then they must have some meaning, and therefore we don't put in characters because characters don't have an inner meaning. You need something that has an inner meaning, so we do a tokenization, and we say some words can have assigned meanings, and so we first make words out of text, and then we identify meaning of these words. But how do we create these meanings? And these are the embeddings. So I made an example for the embeddings. I have three groups of text, of words. I have vegetables, I have emotions, and I have operation systems. So operation systems, I have many more, but in a high-dimensional space, they create groups to each other because they belong to each other, because they have similar meanings. And I don't have a high-dimensional room here, I have only 3 dimensions, so you can think of a cube, and in every corner of that cube are groups like emotions, vectors, and operation systems, and they don't have anything to do with each other. So if you would compute the cosinus distance, the cosinus distance would be 0 because they are orthogonal to each other. The one exception I have taken the word fun and moved it a little bit along to the operation system dimension. So fun and Linux operation systems have something in common. That's what it expressed. And the cosinus distance is not 0. So if you want to do this with a large amount of tokens, you need more dimensions because the dimensions have all some kind of meanings. So 2012, we see Geoffrey Hinton here, and on the left side, Ilya Sutskever. Ilya Sutskever was went later to Google, and when he was at Google, he was asked by Elon Musk if he wants to be a part of the foundation of OpenAI. He said yes. So I think he's the one who created ChatGPT in the core team. There are other people who have contributed, but I think he's a key position in this. And this team had the first was the team that had the idea first to use GPUs for computation. So this is another milestone, and it's kind of Geoffrey Hinton. All the students from Geoffrey Hinton have been contributed to this research. So now we come to the attention mechanism. Then the attention mechanism was invented. It wasn't called it really in that paper. The word attention appears just at one single position, but the attention mechanism was applied to recurrent neural networks, the Schmidt-Huber LSTMs, and it works like this. So, oops. You create something that is called an encoder-decoder. And the idea is that you have 2 streams. One stream is creating tokens. Another stream is influencing the creation of tokens. The encoder has a token sequence with text in French language, and the decoder starts with a start token and is supposed to create tokens that are created because they are influenced by the encoder part. And that part which is doing the influencing is this box here. And this is called the attention mechanism, which is kind of the idea that you have 2 streams of context, and they overlap in some way, and they tell each other how to influence each other. We will see this in detail how it works. So at the bottom here, we have RNNs like LSTMs, and they're creating the token stream. And what happened in 2015 was that at Google, they found out that these LSTMs here have, they need a lot of computation to be trained, and another mechanism could replace them by using the attention mechanism in a special way, which is called self-attention. So you replace these arguments with self-attention mechanisms, where a stream is influencing itself. So this influence from one stream to another can be used by using the same input. A stream that is influencing each other creates memory of the past of the stream. You will see how it works in detail. So therefore, these kind of encoder-decoder constructions don't need LSTMs anymore. Everything is attention, and therefore the paper was called Attention is all you need, and it's not showing them. So, Attention was the name of the paper. So you always see this picture, that's the encoder, that's the decoder. And next thing what happens was that people at OpenAI, they have been working on games so far. And they took this thing and said, wouldn't it be interesting if we omit the input encoder? If we just take this away, we don't use it. We just create, this is the encoder-decoder construction, and we just don't use this anymore. We just use the decoder. So this is the construction of a generative pre-trained transformer, GPT. So how does it work? If we feed in here something, then what we feed in are tokens. And we have here an example. I used in the example sentence the inmost force which binds the world. So if I tokenize them, I can see the colors, which kind of tokens that are, and every token has a number, and these numbers are fed in here, and they are in the beginning translated to embeddings. So left side, this is part of the code from GPT, which GPT-2 is open source. We see that these models have some attributes, they have numbers, and we can see that these decoders, they have many layers. In this case, they have 12 layers, they have 12 times. Then we have a number like a D model, which is the multi-dimension of the embedding. And this is what the transformer does. It takes a token like force, it has the number 2700, and it goes into a small neural network which computes the embedding. It says, okay, the token with the ID 2700, it's like a lookup table, has a specific embedding. And the embedding is has a dimensionality of the D model value. So the vector has 1536 numbers. So this is a vector with the dimension 1536. And the word force is translated into all these dimensions, which have some attributes which create a meaning of force. So it's the fourth token, and the fourth token goes into position 4 in the token position. So then this yellow box is represents the context window of the model. The next thing that happens is a positional encoding. Positional encoding is a strange thing. It assigns every embedding an added value, and that added value shows the model that it is at a specific position in the context. And this positional encoding is a number that is pre-computed. It's always the same. It's just added to the context every time, and it's like a wobbling around the position. The wobbling around the position gives the position in the context depth. So what we have at the end is an encoded representation context. So we go from the encoded representations with the position encoding at the beginning, and what we want to have at the end of the transformer is computed encoded representation at the generation level end of the model. And what we know from the output, all the Zn 0 to 6 are the words from the input. We know this. If the same output comes out, we have the input. But what we don't know is one token that has to be computed. And therefore, the end of the computation of the transformer computation is only one token. We read out only one token, and that's the completion of the sequence, the inmost force which binds the word. Okay? So now something magical must be there in the middle. How do we get from left to right? And I think the best representation is the Chinese moon. So these are these magical symbols which reach a kind of proof something happens, and we get a new token. So you can think of kind of magical books here that are used in some way. They are applied to the context, and it creates this output. So what are these magical books made of? How are they created? So let's consider we have two contexts. We have two contexts called Q and K. And you can imagine that Q is a text and K is a text. So you would ask yourself, okay, but if I want to learn something from these two texts, then, for example, I could ask myself, how is one word in one text related to another? Okay, where are words which have specific meaning? So we can have a kind of lookup table which expresses, okay, these texts have something in common, and they have something in common at specific places. So you must remember that every row is a vector. Every row is a vector, and they are matrices. So if I want to combine these two matrices into a meaning representation, I I turn the matrix K and multiply row with column. Okay. So if I multiply the row with the column, then I have the combination of the first row and the second row of the context K. And because the multiplication of Q0 and K0 is the dot product. So the dot product of these two vectors represent how much these embeddings have in common. Because I get the cosinus distance of these both embeddings. Okay? Because KT is the transposed matrix. Therefore, the row and column are the dot product. Okay? So what I get out of this multiplication is a new matrix which has a relation expression between all of these positions in the text. And because I like the softmax activation on top of it, I also compute the likelihood that one of these words has something in common with the other text. And square root of decay is a normalization of the multiplication. So the softmax works better. Now I have another context B. And another context B is another text where I say, okay, I have this combination of these two texts. I have likelihoods how these words are related to each other. And they are like a lookup table to say from from that other text, I take some embeddings and use them. Okay? So, if I want to learn something, I have to apply some weights, because this is a learning system which applies some weights and say, this relation is something valid, and sometimes it's not valid. I need another matrix which expresses that a text has some valid relations between tokens and other ones don't have this. So these gray boxes are these weight matrices. And what I do in self-attention is that all of them, all of these Q, K, and D is the same context. So I multiply a context with the transposed version of the same context. I get a relational matrix and apply this on the same context. That's self-attention. So, and on the left side, we have this magical books. They say, okay, you have some inputs, they relate to each other, therefore we select something from our whole set of possible tokens that we learned, expressed by this weight matrix, and use it as an output of that attention layer. Okay? So what we also do is we tear these matrices apart, because this allows us to do concurrent computation of parts of the matrix. This is called multi-head attention. I don't have only attention, I have multi-head attention. And this is then combined with a combination matrix again. And this is our time symbol. Here, Satskever was asked, what do you wonder most about GPT? And he said that it works at all. So this is a machine which applies understanding using embeddings to a context, creating a new context. And this is one multi-head attention layer, but we have more. We have many of them. And this is just a picture of the thing. We have many more, because we have in GPT-3 we have 96 of those layers, not 4. And we have 128 attention heads, not 6. It's a very large construction. And to be complete, this is not everything which is in between. We also have these feed-forward networks. These are the two-layer networks which takes the output of the attention layer and produces another version of the context. The network needs this to be able to learn faster. So this is kind of what you say, we have abstraction, production, abstraction, production, abstraction, production 96 times. So this is the result. This is the graph from the paper. Attention is all you need, reduced to the one input layer, and everything that happens in between is expressed by this one equation. What I paint is just I try to visualize this, but what we need is the self-attention QKD product, and that's all which creates meaning inside of this chain of computation. So when they are trained, when these networks are trained, a very large amount of data are put inside. This is not the exact amount of data because it's not known, but in 3.5 or 3 was filled in. This is from a different model, GPT J6B, a very old model, older than GPT-3, and they use, for example, the screen part is 20 biggest Wikipedias. OpenText 2 and Pile, these are web crawls. Arxiv is all the scientific publications in mathematics, in physics, and other sciences, medical information, and so on. It's all of GitHub. Bibliothek is all of books. So yeah, there are numbers behind it, and you can take some parts of the data set and train it several times, and that's the training strategy that you apply. And this is a screenshot from the documentation of the OpenAI API, and they gave this example before GPT-3.5 was published. This was a way to use GPT-3. It was not used. It was not published to be a question answering machine. It was just something that can do a completion of text. And the example they gave was this: Q. What is human life expectancy in the United States? A. Yeah, you see this prefix Q, A. Human life expectancy in the United States. This is an example answer. Then two life weeks and then Q again. What is the meaning of life? And what they are doing here is they give a kind of example how text can be completed for the purpose to answer questions, because they give the structure to show how a question and an answer look like, and they show how a question looks like. And the next thing that the model does is, okay, it knows that the next thing to do would be an A. Yeah? Not be an A, because this is an example. This is what the context in the self-attention is producing in this kind of multiplication tables. This relation is known from the current context. So this was called the one-shot prompt. And with the one-shot prompt, you have been able to create question answering machines before ChatGPT 3.5 was published. So you create maybe different style. It's not necessary that you have a Q and an A. You can also say assistant, human, and so on. And this is a kind of few shot prompt. So you have several examples, and the model then answers very confident in the way that it creates an answer. So the idea was that these kind of one-shot or few-shot prompts are part of the training data. So in pre-training, you create a base model, which is like GPT-3, which doesn't know anything about questions and answers, but it can be fine-tuned using kind of question answering text set. And this text set must be of a good quality. It must show how to create quality kind of answers. And in reinforcement learning, the system is then forced to actually give answers, and some voters, human voters, decide if this was done in a good way or in a bad way, and this was then used again to train the model. So 2022, this caused publication of ChatGPT 3.5 as a fine-tuned model. Let's see. Okay. Here. No one calls this says.
Systems are designed in such a way that in principle, it knows nothing about language, learning, intelligence, thought, none.
The idea that it's just superhuman exploiting there's a sense in which that's true.
So we have two opposite meanings about this. One Chomsky, which is a very important person in computer science because he created a basis for the theory of computability. The formal languages has a strong opinion, and we should consider this as very serious. If he says this is not intelligence, this is just pattern matching, this is just glorified autocomplete or glorified autofill. Why? Oh, again. So, this is glorified autofill. While Geoffrey Hinton says, okay, you can say this, but if you predict the next word in a good way, you have to understand the text. You need understanding. Ilya Sutskever made an example, said, if the document reads a story like a criminal story where the detective at the end says, and the murder is, and you want to autofill or autocomplete, then the name, you have to understand the story. This is not a simple task. So who is right? Because if you say Geoffrey Hinton is right, then this means these models actually understand meaning. So in the Sutskever, predicting next word in a text sufficient way to understand the text. Then we have Jan LeCun, who's we know, another student of Geoffrey Hinton. He says something else all the time, many times. He always says prediction is the essence of intelligence. Or the other way around, the essence of intelligence, the ability to predict. So if you put this together, you have the proposition of Shannon who proved this in his work. He said compression is prediction. If you can compress, then you can predict, and the other way around. And we have prediction is intelligence, supported by Hinton and Sutskever. We can combine this. This means compression is intelligence. And think about this. So a zip file is intelligent. Or maybe a LLM model file is nothing else than a zip file. It's compressed information. Is a zip file, has zip file understand many things in a special way? So there's a Hutter prize. The Hutter prize is a challenge where you get money if you compress a specific part that's given. You can download this, a specific part of the Wikipedia, and if it's smaller than the previous winner, you get a part of these $100 million. And the idea is that at a certain point, you can only create smaller file if you understand the content of the Wikipedia. This compression contest, this is what Hutter writes on his page. This compression contest is motivated by the fact that being able to compress well is closely related to act intelligently. So this is an interesting thing, and there are many philosophical questions connected to this. This talk is not connected to it. It was just to discover this kind of question.
Isn't that specifically like, if you think about the way an autoencoder works, where you have smaller hidden layers and you're forcing it to compress, it's sort of making this manifest in a lot of ways.
In every layer, there must be some, it must make sense of something. Right. Like at the beginning of the layers, and you have different languages, they must all be transformed into an abstract construct which represents the meaning of the text in different languages. Because if it would only work for every language itself, it would be very inefficient. And the model wants to be efficient because otherwise it cannot be trained to a target where it works. So at a specific point of these layers, it has some understanding on an abstract level without languages. And then it brings things to relations it's doing an abstraction of things, it's doing more abstractions represent the discovery of meaning. So if you do a constant abstraction to discover meaning, is this thinking? I can't answer this. It's just it's nice to discover these questions along the constructions of such bits. Probably in 5 years, something like a transformer doesn't exist anymore because there's something which is much more efficient. But, so you shouldn't say, okay, are humans just transformers? Because no. Right now, this is a good model, but you can have something else that's better. So these are the extra slides just to show what happens after ChatGPT 3.5. Only 1 month later, university said, okay, they created these large language models by creating these instruction sets. So let's create instruction sets by harvesting this out of ChatGPT. They created a lot of topics, they created artificial questions and answers, and they created created instruction set which can be used to train your own language model, because base models have been known at this time, but not question answering models. And if this was possible, then Meta published that they are working on this. Only 2 months later, another month later, they provided some kind of base model for scientists, but they didn't think about a good publication way, and then there was in this repository a pull request saying save bandwidth by using a torrent to distribute more efficiently, which means you put this torrent in the pull request, and that was the Llama leak. That was the time where the first model available, first public available model was available for all people who wanted to use something with this, and then this instruction set was used to train question answering model, which was then called Alpaca, Stanford Alpaca. Yes. Only some days later, and then there was an inference engine in C++ written. This was hacked in the evening. I have no idea if it works correctly. It is one of the most well-known inference engine that you can now run on your computer, and also on CPU works very well in a framework called Llama. And tomorrow there's a talk. I give a talk there. Show this how you can use this on your computer. And that's it. I hope it was understandable and sufficiently done. Even if there are some magic parts, but even the scientists say it's magic, and we wonder about it. So if you want to have the slides, go to my social media accounts and I posted a link to the slides. Do we have time for questions? Yes.
I have one question. So, if I am not mistaken, especially in the beginning of ChatGPT was bad at math, but it's basically all math. Why is it bad at math?
So math requires that you have some tokens which have meanings. So if you have just numbers, every number has a single embedding, and every other symbol that you need in math has its own symbol. If you don't have tokens on that can be assigned a meaning to it, then the learning doesn't work so well. Now the models can use better math because they are much bigger. This was a small model related to what's around today. Training data is much more, and yeah. But they still can do so good math. Yes, and can be much better. But on it's not a good representation on token level. they can do very well symbolic math, but not computation.
But it's still the same mechanism, even so it's better now, it's just bigger.
Yes. There are small modifications, but the principle is the same. Thank you. Yes.
Just kind of follow on from this question. See if this module is which is if you just use ChatGPT, it becomes very obvious because you can just put these maths and I just won't be able to actually solve them. Doesn't prove that it really is.
Yes, it supports it, but it doesn't prove it. I would say, yeah, but it supports it, yes. Yes. And for Pomsky and for the next year. All right.